Welcome to my channel. Today we're going to explore one of the most fundamental algorithms in machine learning, linear regression. This is the algorithm that powers everything from simple trend predictions to complex financial models, and understanding it deeply is essential for any machine learning practitioner. Think of linear regression as finding the best straight line that describes the relationship between your input data and the output you want to predict. Imagine you have a scatter of data points representing, say, house prices based on their size. Linear regression finds that optimal line that passes through these points in a way that minimizes the overall error. The equation we use is y equals m times x plus b, where y is your predicted output, x is your input feature, m represents the slope, which tells you how steeply the line rises or falls, and b is the intercept, which tells you where the line crosses the y-axis. This simple yet powerful formula is the foundation of supervised learning and serves as the building block for understanding more complex algorithms.
Now let's dive deeper into the linear equation y equals mx plus b and really understand what each component means. The slope, represented by m, is the rate of change. It tells you exactly how much y changes when x increases by 1 unit. If your slope is 2, then for every unit increase in x, your prediction increases by 2. A positive slope means the line goes upward from left to right, while a negative slope means it goes downward. On the other hand, the intercept, b, represents the starting point, the value of y when x equals 0. Think of it as where your line crosses the vertical axis. Together, these two parameters completely define any straight line in two-dimensional space. When we train a linear regression model, we're essentially searching for the optimal values of m and b that make our line fit the data as closely as possible. The magic happens when we realize that with just these two numbers, we can make predictions for any value of x, even values we've never seen before. This is the power of generalization in machine learning.
Let's explore the two main types of linear regression, simple and multiple. Simple linear regression uses just one input variable to predict the output. The equation is y equals beta 0 plus beta 1 times x, where beta 0 is the intercept and beta 1 is the coefficient for our single feature. This creates a line in two-dimensional space, and it's perfect when you have one clear predictor, like predicting house price based solely on square footage. But what happens when price depends on multiple factors, like location, number of bedrooms, and age of the house? That's where multiple linear regression comes in. The equation extends to y equals beta 0 plus beta 1 times x1 plus beta 2 times x2 and so on for as many features as you have. Instead of fitting a line, you're now fitting a hyperplane in multidimensional space. While we can't easily visualize dimensions beyond 3, the mathematical concept remains the same. Each coefficient tells you the effect of that particular feature on the prediction, holding all other features constant. This ability to handle multiple inputs is why linear regression remains a workhorse in real-world applications. Now we need to understand how we measure the quality of our predictions, and this brings us to the cost function. The most common cost function for linear regression is mean squared error, or MSE. Here's how it works. For each theta point, we calculate the difference between what we actually observed, y, and what our model predicted, y hat. This difference is called a residual. The problem is that some residuals are positive and some are negative, so if we just added them up, they might cancel out. To fix this, we square each residual. This makes all values positive and has another important effect. It penalizes larger errors more heavily than smaller ones. An error of 10 gets penalized 100 times more than an error of 1. Finally, we take the mean of all these squared errors to get a single number representing how well our model fits the data. The formula is j equals 1 over n times the sum of yi minus y hat I squared. Our goal during training is to find the parameters m and b that minimize this cost function.
The lower the MSE, the better our model fits the training data. This cost function is what drives the entire learning process.
So, how do we actually find the minimum of our cost function? This is where gradient descent comes in, and it's one of the most important optimization algorithms in all of machine learning. Imagine the cost function as a bowl-shaped surface, like a valley surrounded by hills. Your goal is to find the lowest point in this valley, which represents the parameters that minimize error. Here's the intuition. Imagine you're blindfolded and dropped somewhere on this surface. How would you find the lowest point? You'd feel the slope under your feet and take a step in the direction that goes downhill. Then you'd repeat. Feel the slope, take a step downhill, feel the slope again, take another step, and so on until you reach a point where no matter which direction you move, you'd be going uphill. That's the minimum. Gradient descent does exactly this mathematically. At each iteration, it calculates the gradient, which tells us which direction is steepest, and takes a step in the opposite direction. The size of each step is controlled by a hyperparameter called the learning rate, often denoted as alpha. Too small a learning rate, and you'll take forever to reach the minimum. Too large, and you might overshoot and bounce around, never converging. Finding the right learning rate is crucial for successful training.
Now, let's look at the mathematics behind gradient descent. We have two update rules, one for the slope, m, and one for the intercept, b. The rule is m equals m minus alpha times the partial derivative of j with respect to m. Similarly, b equals b minus alpha times the partial derivative of j with respect to b. These partial derivatives tell us exactly how much the cost changes when we make a tiny change to each parameter. For the slope, m, the partial derivative works out to 2 over n times the sum of x sub I times the difference between predicted and actual values. For the intercept, b, it's simply 2 over n times the sum of prediction errors. Let me walk you through a concrete example. Say our learning rate, alpha, is 0.01, and we calculate that the partial derivative with respect to m is negative 4.5. This means increasing m would decrease our error. So we update m by subtracting alpha times negative 4.5, which means we add 0.045 to our current m value. Before, m was 0.5. After the update, it's 0.545. We repeat this process thousands of times, and with each iteration, our cost, j, decreases. The gradient acts as a compass, always pointing us toward the direction that reduces error most quickly.
There's actually another way to find the optimal parameters, and it doesn't require any iterations at all. It's called the normal equation, and it gives us a direct, closed-form solution. The formula is theta equals x transpose x inverse times x transpose y. Let me break this down. X is your feature matrix containing all your input data. X transpose is that matrix flipped on its diagonal. Y is your vector of target values. When you multiply x transpose by x, you get a square matrix. We then invert this matrix and multiply it by x transpose y to get theta, which contains all your optimal coefficients. It's like a helicopter dropping you directly at the lowest point instead of hiking down the mountain step by step like gradient descent does. Sounds perfect, right? Well, there's a catch. Matrix inversion has a computational complexity of O of n cubed, where n is the number of features. For datasets with tens of thousands of features, this becomes prohibitively slow. Also, the matrix X transpose X must be invertible, which can be a problem with highly correlated features. So here's the rule of thumb. Use the normal equation when you have fewer than 10,000 features and gradient descent when working with larger datasets or when you need online learning capabilities.
This section is critical for anyone preparing for data science interviews at top tech companies. Linear regression comes with 5 key assumptions, and violating them can make your predictions unreliable. First is linearity. The relationship between your features and target must be linear. If the true relationship is curved, a straight line simply won't capture it well. Second is independence. Your observations must be independent of each other. This is often violated with time series data, where one observation depends on the previous one. Third is homoscedasticity, a fancy term meaning that the variance of your residuals should be constant across all values of x. If your errors fan out like a funnel shape, that's heteroscedasticity, and it violates this assumption. Fourth, the residuals should follow a normal distribution. This matters especially for confidence intervals and hypothesis testing. Fifth is no multicollinearity. Your input features should not be highly correlated with each other. When features are correlated, it becomes difficult to determine which one is actually driving the prediction, and your coefficient estimates become unstable. In interviews, you'll often be asked to name these assumptions and explain what happens when each is violated. Make sure you can diagnose each problem and suggest appropriate remedies.
Once you've built your model, how do you know if it's any good? This is where R-squared comes in, and it's one of the most important metrics for evaluating regression models. R-squared measures the proportion of variance in your target variable that is explained by your model. Think of it this way. Your data has some total amount of variation measured as SS total, the sum of squared differences from the mean. Your model explains some of that variation, which we call SS explained, and the rest is unexplained error, or SS residual. R-squared is calculated as 1 minus the ratio of residual variance to total variance. An R-squared of 0.85 means your model explains 85% of the variance in your data, which is generally considered quite good. R-squared ranges from 0 to 1, where 1 would mean perfect predictions. But here's a crucial caveat. R-squared always increases or stays the same when you add more features, even if those features are completely irrelevant. This can be misleading. That's why we also use adjusted R-squared, which penalizes you for adding features that don't improve the model. If your R-squared is 0.85, but your adjusted R-squared is only 0.7, that's a red flag that you may have added irrelevant features. Always report both metrics when evaluating your models. Let's talk about one of the most important techniques for preventing overfitting, regularization. When your model fits the training data too perfectly, it often fails to generalize to new, unseen data. Regularization helps by adding a penalty term to your cost function that discourages large coefficient values. There are three main types you should know. First is ridge regression, also called L2 regularization. It adds lambda times the sum of squared coefficients to your cost function. This shrinks all coefficients toward 0, but never actually makes them 0. It's great when you have many features with small, cumulative effects. Second is Lasso regression, or L1 regularization. Instead of squaring the coefficients, it uses their absolute values. This has a remarkable property. It can shrink coefficients all the way to exactly 0, effectively performing feature selection automatically. Use Lasso when you suspect only a few features really matter and you want to identify them. Third is elastic net, which combines both L1 and L2 penalties. This gives you the feature selection ability of Lasso while maintaining some of Ridge's stability, especially useful when features are correlated. The lambda parameter controls how much regularization is applied. Higher lambda means more penalty, simpler models, but potentially higher bias. Finding the right lambda through cross-validation is key to building models that generalize well. What if your data has a curved relationship that a straight line simply cannot capture? This is where polynomial regression becomes incredibly useful. The key insight is that linear regression refers to being linear in the parameters, not necessarily in the features. You can transform your input features by adding polynomial terms. Start with your original feature x, then add x squared, x cubed, and so on. The equation becomes y equals beta 0 plus beta 1x plus beta 2x squared plus beta 3x cubed. Now your model can fit curves. The beauty is that mathematically, this is still linear regression because we're still solving for linear combinations of coefficients. We've just transformed our feature space. A degree 2 polynomial gives you a parabola. Degree 3 adds inflection points. Higher degrees create increasingly wiggly curves. But here's the critical warning. Higher polynomial degrees lead to overfitting. Your model might pass through every training point perfectly, but it will perform terribly on new data because it's memorizing rather than learning generalizable patterns. This is the classic bias-variance trade-off. Underfitting means high bias, your model's too simple. Overfitting means high variance, your model's too sensitive to training data noise. The sweet spot is usually a low-degree polynomial, typically 2 or 3, combined with regularization. Use cross-validation to find the right combination.
Let's wrap up with a quick review of everything we've covered, perfect for your interview preparation. When asked about the cost function for linear regression, remember it's mean squared error. 1 over n times the sum of squared differences between predictions and actuals. For optimization, know when to use each approach. Normal equation works beautifully for smaller datasets with fewer than 10,000 features, giving you an exact solution immediately. Gradient descent scales better to massive datasets and is essential for online learning. The 5 assumptions you must memorize are linearity, independence of observations, homoscedasticity or constant variance of residuals, normality of error distribution, and no multicollinearity among features. For regularization, remember that Ridge shrinks coefficients but keeps all features, while Lasso performs automatic feature selection by pushing some coefficients to exactly 0. ElasticNet combines both when you have correlated features. Use R² to measure how much variance your model explains, but always pair it with adjusted R² to account for added features. These concepts form the foundation not just for interviews, but for your entire machine learning journey. Linear regression may seem simple, but mastering it deeply prepares you for understanding more complex algorithms built on these same principles. If you found this video helpful, please like and subscribe to the channel for more AI engineering content. Thanks for watching.